Okay, this one is actually a reshoot. I had actually misremembered one of the formulae, which is kind of sad, but these things do happen. So I'm reshooting both this example video and the relevant concept video. So it should be all correct and accurate by the time you get to it. This is stuff for a couple of weeks hence. But yeah, hopefully it hasn't confused too many people. So let's have a go at this example. We've got a circular track, or at least this section of it has a circular type of section with a radius of 20 meters. Okay, we know that we've got the car on the track going this way. We don't know its velocity v, so v is a question mark, we're not sure. R is 20 meters. M, the mass of the car, is 1270 kilograms. What else are we told? Okay, we're told that omega, the rotational velocity, is 0.7 pi radians per second, because we tend to work in pi's, but pi is just a number, so we could also say is 2.2 radians per second if we calculate that out. Right? So we've got those things, and what we want to know is the centripetal force. So we need F is a question mark, newtons, I should put units for that as well, meters per second. So to get to that, to get to a centripetal force, we're going to instead use Newton's second law, F equals ma. F equals ma. Now we need to find the acceleration. So, sorry, something I should have probably said earlier. We have a lot of unknowns here. We're not going to bother with calculating the velocity. We could figure out the velocity. We could figure out that it's going around at 2.2 radians per second, and we know the radius, so we could figure out the circumference of the circle and how much it's fast it's traveling and so on. But that's a little bit of a faff for our purposes when we already have omega. And we have an expression which says A equals R omega squared. This formula is the one that I misremembered, but hopefully you have never seen it wrong. So this is the correct one, and I won't confuse you. But A equals R omega squared. In other words, the radius times that rotational speed squared. So we can sub that value of A into Newton's second law. So let's give ourselves a little bit of room. F equals mr omega squared. Now, one of the things that's quite useful is that we do have multiple ways of doing problems. As I say, we could have found V if we wanted to, but given that we're already given omega, and it would be a bit of messing about to find V, we're not going to bother. So we can find that centripetal force now because we know all of the things in this equation. So is equal to the mass, which is 1270, times the radius, which is 20, times the omega, which is 2.2 squared. And if we run that through the calculator, we get 1.23 by 10 to the 5, and we're talking forces, so our units will be Newton. So 1.23 by 10 to the 5 Newton is the centripetal force that's acting on the car to make it accelerate. We could calculate, let's calculate just what the centripetal acceleration is, because that's kind of interesting, I think. So A equals R omega squared. We just want to know what the centripetal acceleration is, because then we can figure it out in terms of G's, of cornering forces that this car is experiencing. So 20 times 2.2 squared is 96.8 meters per second. If we divide that by 9.8 to get it in Gs, we find that it's almost 10 Gs. It's about 9.9 G. That is ridiculous. This driver has completely passed out. Humans pass out at about 6 or 7 G, even with pressure suits on. So this may not be a completely realistic problem, because the cornering forces are just too big, only probably a couple of orders of magnitude. Maybe if it had been 0.3 pi radians per second that the person was travelling at instead, it would be a survivable question. And of course, that assumes that the tyres can stick to the road with those kind of forces, which they almost certainly can't. So it's perhaps not a particularly realistic problem, but it is one where we've actually been able to calculate what that centripetal force is based on the mass, the radius, and that rotational velocity.